Welcome to another lecture on ECEN 215. Today we're going to discuss AC signals. This is going to start a shift in the class where we're now moving away from doing analysis on just DC voltages and current, and now look at signals that are alternating in value, particularly by a sinusoid. So let's just go ahead and get started. First, we're going to bring back a slide we had earlier in the semester in which we showed what AC looks like. So just as a kind of refresher, this is from lecture 2, the two different types of current we have. We have DC current, we have AC current, where DC current is just a static voltage, or in this case shown as actual current, that is just over time it's the same value. So it could be, in this case, it's 2 amps from, in theory, minus infinity to positive infinity in time, and there is no time component to the value. Whereas with an AC signal, being either an AC current or an AC voltage, the signal has a period and a waveform, and here we're actually showing a waveform that is defined by a cosine. So that just give you an idea of what we are talking about. So we're not going to talk about signals that now have a period, a frequency, and an amplitude. So let's go ahead and take a look at that a little bit more in depth and detail here. So what we have here is the signal we were just talking about, where we have plus or minus a magnitude, so Vm. So this is because a cosine term is plus or minus 1. So if you want to amplify that to say, we were just showing a moment ago something that was on the neighborhood of 2 amps. So if Vm was 2, or 2 volts, for instance, Vm was 2 volts, then this signal would alternate between minus 2 to positive 2. And it does so over a period of time that this waveform will repeat itself. And it will be offset by maybe some static value. That's kind of a superimposed waveform. But in this case, it is across the zero axis. So just simply put, an AC signal is this component that is alternating back and forth at some particular period. Now, the frequency, basically the repetitive nature of this is set by the fact that we have omega, which is the frequency, and t, this period, must be defined by 2 pi, because this is this cosine term here, particular may be in radians, and then of course we can have some offset angle given a degree. So in the end, you're pushing a value through cosine, and you're just alternating back and forth. So frequency is how often this actually takes place, and that's just 1 over the period. You probably remember this from physics. So these formulas are very important to remember because you're going to see this over and over again. You're going to be told, given a waveform, a cosine waveform or sinuside waveform of 60 hertz, which is the frequency of the power frequency here in the United States. What is the period? And what you would do, so you're told frequency is 60 hertz, and you would take 1 over 60, and that will give you the period. How many seconds does it take for it to go from one peak to the next peak? So basically the entire period for the signal to repeat itself. And in the case of 60 hertz, that's about 16.66 milliseconds to do that. So your standard AC waveform for power is 16 milliseconds between this point and this point in time. Omega, which is in radians per second, is defined as 2 pi over t. Or you can also, if you need omega, and you're given F, you just multiply by 2 pi and you will get omega. So if you're working out the actual formula for wall current, for instance, and we'll talk about this a little bit more in detail, but for your standard household appliance here in the United States, which is 120 volts RMS, and we'll be talking about what that means here in a moment, VM is actually about 165 volts times cosine of 2 pi 60 plus, and if there is a phase offset, but you can assume that if you just assume the phase starts at 0 degrees, then it would just be 2 pi f, where f is 60. Here we show the AC waveform here of 100 volts peak to peak. So we go from minus 100 to 100 volts. We have an AC waveform. It starts at a cosine. Cosine of 0 is 1. So this is plus 0 degrees. So we would end up, and this is approximately roughly 10 milliseconds to 30 milliseconds. So this approximately has a 20 millisecond period, which immediately tells us, we go 0.02, 1 over x, tells us we have a 50 hertz waveform. If I wanted to know the radians per second, if I was going to write out this equation for this signal, so we have plus or minus 100 volts, so Vm is equal to 100, and then you have no offset because the cosine starts at 1, so that means the theta, or the offset angle, is 0, and then we only need is omega t. Omega is 2 pi f, so we take the 50 hertz, multiply by 2, and multiply by pi, and we end up with approximately 314.15 radians per second. So this signal right here mathematically is 100 cosine 314.15 approximately times t. And you could completely describe this signal. Power can also be described in a similar fashion. In this case, the average power is about 100 watts. Notice that power is always positive for this particular signal, which immediately tells us that this is being absorbed because power is always positive. It's not across the zero axis. So that brings us to one of the things. A moment ago, I talked about this value of VRMS, root mean squared. Like for instance, our household current here in the United States, the power that's typically like in the plug that is in your wall of your apartment, or that's probably in most laboratories or in your house. That plug is typically 120 volts RMS. That is what they mean is the effective value. That signal actually is plus or minus peak to peak about 165 volts. So just to kind of give you an idea of that, so this is a periodic waveform, and there is actually an equation for determining root mean square or the effective value of any periodic signal. Now we're about to discuss sinusoids or cosine terms, but just this is the formula for any periodic waveform, whether it be a square wave, triangle wave, trapezoid wave, or sinusoid. This is the formula for that. It is the square root of 1 over t, where t here is the period, and you're integrating the period of the voltage if you're solving for voltage IRMS. Of course, you would do the same thing if this was current, IRMS. You would just replace this with I, or power, so on and so forth, be with V times I. So you take the square root of 1 over t, and you take an integration of 0 to t, being this is still the period, of your waveform over time. If you integrate that, you will get the voltage RMS. So if we take our signal, and what we had earlier was the 100 cosine omega t, and if you do that, there's a very simple formula for sinusoids, and that is just simply the magnitude divided by the square root of 2. Now you can go through the calculus on that and determine it, but this is for simple sinusoidal values. This is the formula for that. So that's how we get 165 volts. So 120 volts RMS times the square root of 2 gives us a magnitude voltage of, actually it's 169.705 volts. So that is the peak-to-peak signal actually coming out of the wall, if you will, for the actual signal. That is important to note because when you are designing systems and choosing capacitors for like air conditioners and things like that, or looking at a system that is taking household current and going to transform it, and there may be capacitors on the line in various forms, you have to pay attention to the peak value of those voltages. So you would not pick like a 130 volt capacitor, you would blow the capacitor because the actual peak voltage on the signal is 169 volts versus the effective value being 120 volts. So, and I'm going to be covering this a little bit further in the next part of this lecture, which deals with a new topic we're going to call phasers. Um, so here, just so that we see this right here, we have 150 volts peak to peak, um, and we have a signal that the RMS value actually is more around 106 volts. So take 150 volts divided by the square root 2 gives us 106. So again, I'm going to be covering this again in the next part of this lecture dealing with phasers. Um, we're going to be introducing these new mathematical concepts for describing AC signals. So first of all, you may have remembered from some of your algebra lectures back in high school and probably a little bit in calculus, we have an imaginary number. Um, and where it is actually the square of that happens to be a -1. Because if you try to take the square root of -1 in the real domain, it is undefined. So I squared is defined as being -1. Now, one thing you may have noticed is we use the letter I in electrical engineering to represent current. And the reason for that, by the way, I think I mentioned this in an earlier lecture. The reason why we call that is because there's the French phrase for dealing with intensity of current, and I won't bother you with my poor French, um, but it was because the research scientist Ampere is the one who he was French, and he defined first the discovery of current. And because of that, we've named the units of amps after him, and the number or the units of current after him in terms of amps. And because of that, we use the letter I to represent intensity of current. As such, using the letter I for the imaginary number becomes a little bit problematic, and so hence we now use the letter J to represent that. So physicists, in all of your physics lecture, if you ever had any imaginary numbers, it would have been everything in using the letter I for the imaginary number. For everything in this class, and anytime you work with electrical engineer and they do anything, you're going to see the letter J, just the way it is. So this deals with the fact that AC signals by having this circular nature. In other words, they're periodic. They are following a circle effect in essence. And because of that, we use a thing known as Euler's formula. And this here, for this class, you don't need to know Euler's formula, and we're not going to use it to actually do any mathematical processing here, but we're going to show you here why we end up using the imaginary number. Where is the mathematical basis for this? Because as we were just talking about, we have cosine terms and sine terms describing these waveforms. Well, that's because in Euler's formula, we can actually define the sine and cosine in the terms of imaginary numbers. He determined that, Euler did, that if you take the exponential of an imaginary number, jx, where x is representing t, for instance, time, but in general, just e to the jx is equal to cosine x plus j sine of x. There is a real term and an imaginary term that represents this. And so cosine, for instance, the real term is e to the jx plus e to the minus jx over 2. And then, of course, correspondingly, we have an imaginary term. Because of this, this works out basically as the formula for a circle. And you can, have these periodic signals because of that. So because of Euler's formula, this is why we use imaginary numbers. We're going to show in the next lecture where this takes off, and we now introduce a new concept called phasers and how to represent AC signals other than just giving the time domain function, the cosine terms. So this introduced AC signals to you so that you have an understanding of the concept that we have now are going to have a signal that is periodic in nature, has a frequency and a phase shift, some angle off of the x-axis to represent this cosine or sinusoidal term. So in summary, today we showed the concept of AC signals. and how we're going to make this transition from everything being in DC to now we're going to be doing the circuit analysis using sinusoids or cosines as our basis for the mathematics behind everything. And as such, we also talked about another way of measuring the magnitude of a signal by using something known as the root mean squared, which is more or less the effective voltage or effective current for a signal and the formula for governing that. Now, it's real important, just as a side note, there are some homework in which we actually have you compute the root mean squared of various signals. And it's very important that you use the formula as you've seen earlier, where it actually involves the calculus, where you're taking the integral, where the formula is equal to the RMS of a signal is the square root of 1 over t times the integral of, say, the voltage squared of t dt. So very important that you pay attention to the calculus on this. The calculation of, for instance, a cosine signal just being the magnitude divided by the square root of 2 is still true, but you've got to consider what that means in a broader aspect of a particular signal. So if a signal is including a DC component, for instance, or a triangle waveform, or a square wave waveform, you do have to apply the formula. It's an easy calculus to do because, like in the case of square wave, it's effectively a constant, so then it just becomes a times t, but you do need to apply the actual calculus that's involved there. And then we talked about Euler's formula, about how we introduced the concept of how do we go from all these trigonometric functions, sines and cosines, to now working with J, the imaginary number that we're going to be using in this course. Instead of the letter I, we're going to be using letter J. So we've introduced now, we're going to be working with imaginary numbers and really more importantly, complex numbers. You're going to have a real component and imaginary component moving forward.